Today we're going to look at the ELF file, and even better, we're going to check out how to patch the ELF file to make it do exactly what we want to do. So we went ahead and grabbed this Hack the Box challenge off HackTheBox, and it's called Gopher Part 1. So the challenge is to reverse engineer it to the point where we get the HackTheBox flag, and we would put it into HackTheBox form saying that we got the flag, give it challenge difficulty, hit submit flag, and we would get points and hack the box. So that's what we're going to do today. So they're going to give us an ELF file. We're going to reverse engineer it, and we're going to look for that tag that says HTB and then some sort of key inside of it. So we are going to be playing with Hack the Box, but this isn't a lesson. This isn't a lesson on Linux operating systems. This isn't not a lesson about ELF files, Ghidra, or Radar. This is going to be a walkthrough. Hopefully I'll give you enough information so you can follow along at least. All right, so here are the tools. Here are the toys I'm going to be playing with. We already got Hack in the Box, and that's where I got the binary file from. But I'm going to be using Ubuntu, then I'm going to be using Ghidra, then I'm going to be using Radar. And also some of the other tools I'm going to be tinkering around with today is file, strings, bin walk, hex dump, and strace. All these are on the Linux distro itself. All right, so since we're doing the HackBox challenge of this ELF, and you already know from the title we're going to be patching it, we need to dive in a little bit deeper about what is the ELF and what we're expecting. This one's a little bit different. So the ELF file is a normal program. Think of it as an exe in Windows. You double click on it, it runs a program. Same thing in Linux. Some of them you can double click, but most of them you're going to have to run inside of the command prompt or the terminal. So when we zoom in, we see that the first thing that it does is it says what type of file it is. And this is an ELF file, ELF. And it does it by passing the hex code 7fox45 4Charlie46. And then it moves on to tell us what bit it is, or what size it is, and this one's going to be a 32. And then it tells us what Indianness it is. So 0101 tells us it's a 32-bit little Indian. And then there's some other 01s and 00s after that. So we kind of just want to take a look at exactly how this ELF file looks. Get an idea, get warm and fuzzy with it, because we're going to be looking at that later. So in order to see what the bad thing looks like, we need to go back and see what the good thing looks like. Let's look at a valid ELF file, and then we can look at that and we can compare it to what we've got from Hack the Box. All right, so let's jump into it. All right, I'm in my Ubuntu machine, and here I got both Gopher and I got Python 3.8. So we're going to go ahead and run a file on Python and see what we get. When we run file, it tells us it's a 64-bit least significant byte executable, so little Indian, on the x86 type architecture, and a lot more information. All right, so if we were to also let's do a strings on it. If we were to strings, tack in, let's go with 10, and then let's see, Python 3.8, and then let's also just look at the head of it. When we do that, we see that Python does have very easily human readable strings. If we were to do a hex dump on it, let's look at the head, we'll see, once again, we have the ELF header right there. It says ELF of 7fox45 4Charlie46. Then we can see that there's a 02 to show that it's 64-bit, and a 01 for little Indian, and then everything else there is either a 01 or a 00 for the first couple of lines of the binary. And then what we are also going to take a look at is the bin walk. If we were to bin walk this, we would see that there is quite a good amount of different sections. So let's go and do those exact same steps. Let's do it with our Gopher that we got from Hack the Box. So found Gopher, it just says it's an ELF 32-bit. No more information than that. Let's go ahead and see what strings it has. And when we do strings, there's nothing there. Let's go ahead and do a hex dump with tag C. And when we do a hex dump with tag C, we see that ELF is there. We clearly see it's an ELF file, ELF. We got the same hex bytes as before, 7 Fox 454 Charlie 46, 01 to show that it's a 32-bit, but the little Indianness is a 61 in hex. That doesn't compare to anything else. That's why we were unable to do a proper file command on it and see what the file is, because the header is garbled with a whole bunch of gibberish that we did not expect. And then last but not least, let's do a bin walk. Let's bin walk Gopher. Once again, nothing shows up. So we can go ahead and take a look at what we had previously, in which this up here is what a good executable looks like, where Gopher that we have, it isn't matching up. So when we zoom in and take a look at the hex dump of Gopher, we see that in that blue square, it's supposed to be something along the lines of 0101, 01000000, but that is completely different. We get 01 for the 32-bit, but everything else in that blue square, it doesn't match up to what we expect we would see. All right, so let's go ahead and run this. We're going to do an strace, then we're going to throw it in Ghidra, then we're going to do a radar. All right, let's go ahead and clear this out. Before we run our strace, let's just run it as is, just straight out as the program. Let's type in the name, hit enter. Nothing happened, at least nothing that we can see. So if we were to run an strace is going to show us every time it makes a system call. So let's do strace on Gopher, see what we have. Strace, Gopher, bam. All right, so we can see that it does execute Gopher, and then it starts looking at the process that Gopher is running on, and then Gopher just merely exits. That's all that it does. It exits. So we are getting absolutely nowhere with strace. So I am a very big fan of using Ghidra. So that's what we're going to do. We're going to take Gopher and drag him over into Ghidra. All right, we got ELF, we got x86, Little Indian. It might not detect Little Indian because everything was garbled, so you might need to go in here in language and select the proper one. But we are going to be working with 86, Little Indian. Most executables are Little Indian. 32-bit, default in GCC. Going to open that up, hit OK here. And then we're going to double click on Gopher, or click on the little dragon. He's cute. All right, this has not been analyzed. Let's analyze it. Yes, yes, click analyze, click yes. All right, and then it drops us into here. So here we got the entry, and in the entry, it immediately jumps to function 8127. I'm just going to call it function 127. So as soon as it starts, it jumps to a function. All right, well, let's go ahead and scroll down and see what the function is. Here's all the gibberish, bunch of gibberish between the jump command and the actual function itself. But if we keep scrolling down, we keep scrolling, here we go. Here is 127, and here's what it does. If we look, we see it does an XOR of AL, and then it increases AL, and then it puts this hex number into BL, and then it calls int80. And then it does the same thing again, moving something into the AL registry, except it moves 4 into the registry, then it does another int80. So that is what we see so far. It's not much. It's a jump and then these two hex 80 commands. So if we were to take a look at that in radar, let's go ahead and do Radare2. You can also just type in R2. D for debug, and then let's go Gopher. All right, so we're in here. We're going to hit capital V. We're going to press Shift V to get a capital V, and then P for page over. All right, so let's take a look at it in Radar. And Radar shows us the same thing. It starts off with a jump going to function 127. But here it's a little bit more detailed into what's happening in between the two. But if we scroll down, scroll, here we go. Here in Radar, we got the same thing. It increments the AL and it moves hex 2 alpha, which we see over here is the decimal number 42, moves that into BL, and then it does this hex 80 command again. And then here it moves 4 into AL and does this hex 80 command. So let's dive in and do a little bit more of a deep dive onto what hex 80 is. All right, so in PowerPoint format, in a nice slide for you to see exactly what we did an S trace. We saw that it exited with exit code 42. We threw it into Ghidra, saw that there wasn't much besides those two hex 80 commands, and then we threw it into Radar and saw pretty much the same thing with a little bit more information on what was happening in the center of the program. All right, so those x80 commands, they are what we call a syscall. A syscall is used to make a transition from user code down into kernel code really quickly to do a major task. Pretty much anything that touches a piece of hardware is going to need a syscall for it. So syscall is indeed the int and then the hex code for 80. And that will do a syscall on whatever is in the EAX registry. So if we were to put the number 1 into the EAX registry and then call 080, that would make us exit the program. If we were to put a 4 inside of our EAX registry and then call it, it would give us a write. And where we write to depends on what is inside the EBX register, and what we write depends on what is inside the ECX register. All right, so in code, things are a little bit different when you talk about assembly versus normal code. Normal code as in object-oriented code, C, C++, C#, Python, Ruby, Rust, in which we like to do our functions very, I call it very American. We put in the function and then we put in argument 1, 2, 3, and 4. Like this, we have printf, and then hello as our first argument, and then our second argument and our third argument. Function, argument, argument, argument. But in assembly, it's a little bit differently. In assembly, we put our third argument first, then our second argument. My apologies, we put our third argument, our second argument, then we put our first argument, and then we call the function. Third argument into a registry, second argument into a registry, first argument into a registry, call the function. So that's what we are looking at down here. When we increment AL, we're making AL 1. And then we're putting 2A into BL. And then we're launching our function, which, as we saw before, this is the syscall function. But we're putting AL and BL into there. But when we looked at our previous, when we looked at this, it said that we needed EAX, EBX, and ECX, but we're putting in ALs and BLs. So the way that works is, instead of writing in that we want the letter, let's say 4 for system write or 1 for system exit, instead of just putting a 1 or 4 there and then filling up the rest of the EAX registry with garbage or zeros, instead of doing all that, we're going to tell the processor that we just want to use up this little bit here in the AL. We don't care about the rest. The rest can be garbage as far as we're concerned. We're only going to look at that little bit. And that's what we're going to be passing in. So we only need to worry about changing AL and BL inside of these 32-bit registries. All right, so we've noticed that there is an exit and that the system and that the jump at the very top goes down to the system call for exit. We put in 01 into EAX or AL, And then we put in 2 alpha, which is also decimal for 42, inside of BL. And then we launch that. So we get an exit of 42. But when it comes to the right, we see that we have the EAX, which is 4. We put 4 into the registry, run the system call, it writes. So we put 4 into the EAX, but we don't see an EBX or an ECX or a BL or a CL. That's not very clear as to where it's getting that from, or if it even gets it at all. All right. So what we're going to do is we're going to look at the execution flow, and we're going to go step by step and see if we can understand exactly what it's doing now a little bit more, now that we understand the concept of system calls and EAX, EBX, and ECX. So I am going to continue to use Radar because Radar is looking pretty good today. I'm going to go ahead and bring up Ghidra on the side. All right, so once again, from the top, we got that jump 127 that immediately goes to that system call to exit the program. But if this jump just wasn't there, if it just magically disappeared, what would this program do? And if we look, the next thing would be it increments BL, increments DL, sure, whatever. But then it moves whatever's at this location, it moves it into the ECX registry, and then it calls this function. Same thing, it takes this, moves it into ECX, calls this function. Same thing. It keeps moving things and calling a function. So let's scroll down and see exactly where function 12f leads us. All right, and if we look down here, 80012f puts us right after the syscall for the system exit. So 12f skips over the system exit. It does not exit, but instead it skips over it and comes down here to this pushing of the base pointer and then this moving of the stack pointer to the base. Don't worry about these two for now. Right after that, it moves 4 into AL and then it does that system call, which is the right. But now if we're looking, it has an AL. It does not have a BL, but it does have a CL, namely this ECX up here. So we have our EAX, our EBX, and our ECX. So 4 for the EAX, and then whatever is up here could very well serve to be that EAX since it moves something into, this up here could serve to be the ECX, especially since it takes something, puts it into ECX, and then it calls that function. So when it does come down here, ECX, that registry is filled with something. So if that jump didn't exist, it would go down this entire list one by one, calling this function to print. And since EBX is missing or BL is missing from this syscall, then it's just going to write to the console. That's pretty much what it is if you throw in a null into the EBX. So let's scroll up one more time. And then if you take a look, everything that is being moved is in between 0A and honestly, nothing rarely is higher than 55. I see 0A, but I don't see anything higher than 55, which means everything that is being retrieved to move into the ECX to later on print is coming from up here. It's coming from that garbled header that we took a look at earlier. So the header is garbled for a reason, and that's pretty sweet. So if we were to start the program, get to this entry, and if we were to skip this jump, we would go through the entire execution of the program, printing it out every single time until we finally naturally get to the bottom where the exit is, and then we would exit out. So if all goes well, and if we skip this jump, we should be able to print out every single piece of data that is in those addresses. All right, so we're going to move on to actually patching it. There are many ways to patch it, but I'm a Ghidra guy. I'm going to show you how to do it in Ghidra. So we're going to go ahead and scroll up inside of Ghidra. Just keep scrolling, just keep scroll. Okay, here we go. All right, and man, I love the fact that I can highlight things in Ghidra because this is exactly where we're going to be at this jump, going to function 127. So here in Ghidra, I'm going to right click, and I'm going to click patch instructions. This processor received a rating of gold during its testing. I know, I have an awesome processor. All right, so while it does that, we're going to look at what we have here. So it is a jump, which is going to be Echo 9, and then D6, and then that is what's going to take it down to 127. So what we want to do is we want to zeroize this out. We want to make it disappear completely, so that way it just goes right over it. But if we were to go in here and change E9, D6, if we were to change that to 0, 0, 0, 0, there is a chance that 0 could be the null terminator for a string that might be further up in the assembly code. Or 0, 0 might mess up something that comes after it. 0, 0, it actually does have a use. But there is one opcode that is specifically meant for doing nothing at all. And we call that the no operation opcode, otherwise known as NOP, N-O-P. And then N-O-P is actually the same thing as saying hex 90 in code. So we're just going to type in N-O-P here and hit enter. All right, so let's take a look at it. We got 90 here, but then immediately D6. So the question is if we have done enough. So if we come over here back to your radar, because we haven't changed anything here, it's really easy to see it. We went ahead and made E90 into a no operation code, 90. I'm sorry, we made E9 into a no operation code, which is hex 90. But we haven't done anything to D6. And I'm still not sure about these zeros. I would like to just go ahead and no operation all of them just to be safe. But we haven't quite gotten that far. So let's go ahead and keep on going. And I found out you can do Control Shift and G to really quickly do your no operation code. Control Shift G, let's patch it. All right, next one, Control Shift G, patch it. And there's a chance that these zeros might be okay. I just don't want to chance it. 90s are perfect by me. So if we see we got 90s all the way down, and then we got FEC3, which over here, FEC3, increment BL. I got no reason to no operation that for the time being. So it looks good. We went ahead and knopped everything. So let's go ahead and export this. So what we're going to do is go to File, Export Program. Nope, we don't want it to be a Ghidra zip file. We want it to be, don't want it to be that either. We want it to be raw bytes. Then I'm going to change mine. I'm going to change it to NOP jump, not jump, because we are no operationing the jump. We're getting rid of it. So I'm going to call mine NOP jump. Call yours whatever you want. Let's hit OK. All right, there's the information for it. All right, so over here in Radar, I'm going to hit Q for quit. Then I'm also going to type quit YY. There we go. And then let's see if it's successfully saved. There it is. And what I want to do is I want to throw it into Radar real quick and see what it looks like. So it immediately said that it could not do the X, the executable, because, well, we haven't quite gave it permission to do that. So let's go and do chmod. Let's plus X, and let's plus X no op jump.bin. And then we can try to run Radar again. Here we go. Capital V, enter, and then P for page over. And we can see that the first 5 bits of code, first 5 bytes actually, no operation. It's just going to slide down those no operations until it gets to increment DL. My apologies, increment BL, and then increment DL. And then it's going to continue moving down, taking something from one address and move it into ECX and then print. Take some data, move it into ECX and print. It's going to keep on doing that naturally as it falls down this code. All right, so let's see it in action. All right, if all goes well, we should be able to run our newly patched binary. I'm going to hit the button and hey, there it is. All right, and I'm going to really quickly go somewhere else so you can't see what the code is. So you have to jump in and you have to do everything yourself. Don't go back 10 seconds and hit pause. That's bad. All right, so hey, we've done it. We found out the HackTheBox key, and we learned a lot about elves and how to patch elves. So let's go ahead and wrap it up. So what we did is we found out exactly where we wanted to modify our program by looking at that jump command and realizing that that jump command would be great if it just didn't exist. And we went ahead and made that modification, ran the program, and we got the code. So, and we did that by using Ghidra to do the patch instructions. And then we've got HackTheBox key. All right, so we started off looking at the elf files. We looked at exactly how the very first part of the header is created. And then we inspected a good elf file, Python. Then we inspected the not so good file, the HackTheBox file. Then we looked at the differences in between the two. We looked at SYSCALLS and we determined which SYSCALLS were being used. And then we followed the execution code of the program itself. And we determined where would be best to add in a couple of new operations and how to get rid of that jump and allow the normal execution of the program. And then finally, we patched the file, got the flag. Awesome. Well, I had an absolute blast, and I'm glad y'all were able to join me. So if you have any questions, feel free to reach out to me. Hey, until then, keep hacking the box. Talk to you later.